In 1982, a Soviet lander hit the surface of Venus, stayed alive in lead-melting heat, and snapped the only colour photos we have ever taken from that world. Images one scientist later said show something moving in the frame. This video tears into those pictures. The hardware and the physics of Venus to answer one question. Did Venera 13 really see life in hell? Or are we just staring at a trick of a dying camera? It's early 1982. The Soviet Union is flying the Venera 13 spacecraft to Venus. The cruise stage does the trip through space. The part that matters for this story is the descent capsule and the lander inside it. As the capsule hits Venus's atmosphere, it is going more than 11 kilometers per second, above 25,000 miles per hour. The outer shield heats up so much that it literally burns away to protect what's inside. While this is happening, inside the capsule, the lander is sealed inside a thick, almost spherical pressure vessel. It is about 1 meter wide, a bit over 3 feet. Engineers have designed it to hold out against external pressures of roughly 9 megapascals, or about 92 to 93 bar. They know this is close to what Venus will throw at it near the surface. They also know the air down there is not just hot, it's around 735 to 740 Kelvin, again roughly 460 to 470 degrees Celsius, 860 to 880 Fahrenheit. That is beyond the melting point of lead. It is far above the operating limit of normal electronics. The parachute opens high up, where the air is still thin enough that a parachute works. Deeper down, the atmosphere is so dense that a parachute becomes useless drag, so they release it. The lower descent is just the capsule pushing through thick, hot, heavy carbon dioxide. Sensors are already recording how pressure and temperature rise with depth. Those data later become part of our standard picture of Venus's atmosphere. Then the capsule reaches the surface. It hits hard, but not hard enough to smash the core. A ring of material under the lander is designed to crush and absorb impact. Explosive bolts fire to drop protective covers. The pressure vessel is now sitting directly in that high-pressure, high-temperature atmosphere. Inside, the electronics start at roughly room temperature, but they begin to heat up. There is no way to dump heat into surroundings that are hotter than you are, so the engineers rely on insulation and materials that absorb heat for a short time. Here is the key point. They only expect the lander to last about 30 minutes on the surface. That is the design lifetime. After that, they assume the internal temperature will climb so high that circuits fail and components deform. Instead, Venera 13 operates for about 127 minutes, just over 2 hours. During that time, it sends data back to an orbiter, and from there back to Earth, until finally the rising internal temperature shuts it down. Survival is only one part of the story. The second part is what the probe actually does while it's alive, because if you're going to claim decades later that something moved in those images, you have to understand exactly how the cameras worked and what else was measured at the same time. Here's the hook for that. Most people think of a camera as a device that takes a single instant snapshot. Venera 13's cameras did not do that. They built images slowly by scanning the scene line by line. That detail is a big part of why later motion claims are so controversial. On the outside of the pressure hull, the lander has 2 television cameras. They are mounted low, close to the ground and point in opposite directions. When the lander finishes its touchdown sequence, small explosive charges blow off the lens caps. Then each camera starts to scan. A mirror or prism sweeps across the horizon. As it moves, the camera records brightness information for a narrow strip of ground and sky. The system repeats this, building up a panorama over minutes, not milliseconds. The end result looks like a wide, curved, orange-tinted image. In it, you see a flat plain with scattered rocks, a little bit of the lander hardware, and a uniform, hazy sky. The colours are strange because the thick atmosphere filters sunlight, shifting what reaches the surface. But the important part is that each frame is really a time-smeared construct. If something changed during the scan, that change would appear baked into the final image. While the cameras are scanning, the rest of the payload is working. A drill extends from the bottom, goes about 3 centimeters, or a little over an inch, into a nearby rock and brings up a small sample. This sample is fed into an X-ray fluorescence spectrometer. That instrument tells you which elements are present. The result is clear. The rocks are basaltic, similar to volcanic rocks on Earth's ocean floors and plateaus. That fits with radar evidence that Venus is covered by vast lava plains. Gas analyzers take in the local atmosphere and confirm it is about 96.5% carbon dioxide, about 3.5% nitrogen, plus traces of sulfur dioxide, water vapor, and other minor gases. Pressure sensors report about 92 bar at the surface, roughly what you'd feel under almost 1 kilometer, around 3,000 feet of ocean on Earth. Temperature sensors read around 735 to 740 Kelvin. There is also a microphone system that picks up low-frequency sounds, the thud of landing, the whir and clacks of mechanisms, and a steady wind noise. That wind is only a few meters per second, maybe 5 to 10 miles per hour, but in such dense air even that is powerful. Altogether, the lander's instruments lock in a picture of Venus's surface that is now textbook material. A basaltic, volcanic landscape under an incredibly thick CO2 atmosphere, at temperatures that would ruin most metals and all normal plastics in minutes. So far, nothing about this screams life, it just screams hellishly hostile. So how do you go from this straightforward, brutal environment to claims 30 years later that small shapes in those panoramas might have moved? This jump begins in 2012. Russian scientist Leonid Ksanfomaliti decides to reanalyze some of the old Venera 13 and 14 images. These are not brand new high-resolution files, they are archival data that have already been processed, printed, and copied in different ways over the years. But he treats them as raw evidence for a fresh question. Do any small features change between one panorama and the next? He looks at sequences of images taken at slightly different times. The lander repeats some scans so you can compare before and after views of the same general area. Ksanfomaliti zooms in on the immediate foreground near the lander's base. There he picks out a few shapes that catch his eye. One is a bright, roughly circular object that appears in one panorama and seems to show up in a slightly different position in another. He names it the disk. Another is a dark patch that appears to change shape and intensity between images. He calls this one the black flap. Then there is an elongated, irregular form that, under strong image processing, can be interpreted as a body with extensions. He dubs that the scorpion. He measures their apparent sizes by comparing them to known features, bits of the lander hardware, the distance scaling of the camera, and the size of nearby rocks. Based on that, he estimates that some of these objects are on the order of 10 to 50 centimeters, around 4 to 20 inches, that is big enough to see clearly at the lander's distance. Then he looks at the time interval between scans. We're talking tens of minutes. To him, the fact that these shapes seem to shift position or appearance over that interval suggests that they might not be static rocks or simple noise. In his paper, he does not explicitly claim discovery of life. He uses more cautious wording, talking about objects with features that could be interpreted as life activity and possible manifestations of living organisms. But he is clearly pointing in that direction. He suggests that these changes could be due to the behavior of unknown surface life adapted to Venus's extreme conditions. That leads to the real tension. If even one of these shapes is actually alive, then biology is not limited to the temperature and chemistry window we thought it was. It would mean that some kind of system has solved the problem of operating at around 460 degrees Celsius in dense CO2 at almost 100 bar, with corrosive sulfur compounds present. It would mean membranes that do not fail at those temperatures, information-carrying molecules that do not break apart, and reaction networks that stay stable when normal organic chemistry is being ripped to pieces. On Earth, even the most heat-tolerant microbes lose function far, far below those conditions. Our entire understanding of biochemistry is built around a much milder range. So if Ksanfomaliti is right, life is not just flexible, it is far more general than we thought. and we have been underestimating how many kinds of worlds might be able to host it. But before you accept that, you have to ask a harder, more grounded question. Is Venus's surface even remotely compatible with any life system we know or can realistically design on paper? Or are these moving shapes just the side effects of cameras and data being pushed past their limits in an environment trying to kill them? How bad does a planet have to be before even solid metal starts to behave like warm wax? That's the level you're dealing with on Venus, and you need that picture clear before you decide whether anything anywhere on that surface could crawl, twitch, or even sit still without falling apart. Start with the raw numbers. Down at the surface, Venus sits at about 735 to 740 Kelvin. In everyday terms, that's roughly 460 to 470 degrees Celsius, around 860 to 880 degrees Fahrenheit. Lead melts at about 327 degrees Celsius, so Venus is more than 100 degrees hotter than the point where lead turns to liquid. The pressure is about 92 to 93 bar, which is close to what you'd feel under almost 1,000 meters of water, around 3,000 feet in Earth's ocean. Your body, any normal machine, any exposed material designed for Earth, would fail almost instantly. The air itself is also not friendly. It's about 96.5% carbon dioxide and about 3.5% nitrogen, with traces of sulfur dioxide and other sulfur compounds. At those pressures and temperatures, the lowest part of the atmosphere doesn't behave like the air you know. It's a supercritical fluid. It's not a normal gas, not a normal liquid, but something in between. It can flow like a gas, but dissolve and carry chemicals more like a liquid. That means it can soak into materials and speed up reactions and corrosion. So already you have 3 problems for life and hardware: extreme heat, extreme pressure, and a chemically active, dense medium that can attack most familiar materials. That's just the baseline. So why is Venus this bad in the first place, and how does it stay this uniform day and night? Here's the key point. Venus is hotter than Mercury in many places, even though Mercury is closer to the Sun. Mercury gets more energy per square meter, but Mercury doesn't have a thick atmosphere. Venus does. And that thick CO2 blanket is the whole story. Sunlight comes in as visible light, passes through the atmosphere, heats the surface, and then that surface tries to radiate energy away as infrared. Carbon dioxide, plus a bit of water vapor and sulfur dioxide, is very good at absorbing that infrared and re-radiating it in all directions, including back down. You basically get a permanent feedback loop. The heat can't escape easily, so the whole lower atmosphere and surface warm up until the energy going out finally balances the energy coming in. Because the atmosphere is so deep and dense, it mixes heat very efficiently. Probes and models both show that the surface temperature barely changes between day and night, or between equator and poles. It's not like Earth, where deserts are hot and the polar regions are cold. On Venus's surface, almost everywhere is in that 460 to 470 degrees Celsius range all the time. If the ground is that bad, what happens when you move up into the air above it? Does anything get better, or does it just get worse in a different way? Climb up into the atmosphere. Between roughly 45 and 70 kilometers altitude, you reach the famous cloud layers. These clouds are not water clouds like on Earth. They are mostly tiny droplets of concentrated sulfuric acid with a little water and other stuff mixed in. The clouds are thick, they reflect a lot of sunlight, and they help trap heat below and reshape how energy moves around the planet. Those cloud layers also don't sit still. Venus's atmosphere does something called superrotation. While the solid planet rotates very slowly, one Venus day is longer than one Venus year. The atmosphere in the cloud region circles the planet in about 4 Earth days. That means winds up there can reach more than 100 meters per second, over 220 miles per hour, basically high-speed jet stream levels. Near the surface, the winds are only a few meters per second, maybe under 10 miles per hour, but because the air is so dense, even those slow winds carry a lot of momentum. They can push on rocks and hardware much harder than an Earth breeze of the same speed. So high up you have fast, acid clouds. Down low you have slow but heavy winds in a supercritical CO2 layer. That all sounds hostile, but is there any altitude where Venus looks even slightly like a place Earth microbes might tolerate? There is one band that gets a lot of attention. Around 50 to 60 kilometers above the surface, temperature and pressure cross into a range that, on a simple chart, doesn't look insane. Temperatures there are roughly 20 to 60 degrees Celsius, about 68 to 140 degrees Fahrenheit. The pressure is around 0.5 to 2 bar, so between half and twice Earth's sea level pressure. That's similar to conditions you'd get in low-lying hot desert regions or in a pressure chamber. If you ignore the acid for a moment, those numbers look surprisingly okay for some known Earth microbes. We have acid-tolerant organisms called acidophiles that can handle very low pH. We have microbes that like moderate to high temperatures, so astrobiologists look at that 50 to 60 kilometer layer and say, if Venus has any life at all, this is the most likely place. It would probably have to be airborne, living inside droplets or tiny particles, not on solid ground. That's why modern discussions about life on Venus mostly talk about cloud life, not surface life. The surface is beyond the limits of any known extremophile. The mid-cloud region, while still difficult and very acidic, at least overlaps with the general physical range where some Earth systems can operate. That difference matters a lot when you judge claims about something moving on the actual ground. So then ask the next hard question. If this environment is so destructive even for chemistry, what does it do to human hardware in real time? At about 92 bar and 735 to 740 Kelvin, many metals lose strength quickly. Steel and common alloys start to creep, which means they slowly deform under constant load. Solder joints soften. Lubricants for moving parts either break down or change phase. Electronics heat up far beyond normal operating limits. You cannot cool by radiating heat into a hotter environment, so your only options are thick insulation and internal materials that absorb heat for a short time by changing phase, like melting. That's why the Venera landers were designed for only a few tens of minutes on the surface. Their pressure shells were thick and strong, but they could not stop heat from leaking in. Inside, temperatures rose steadily from the moment the lander touched down. Venera 13 lasting 127 minutes and Venera 14 lasting 57 minutes does not mean the planet was kinder than expected. It means the design was conservative and the hardware took a controlled beating until it crossed a thermal limit and died. Every image, every line of video, every sound sample from those missions came from systems that were literally in the process of failing. Bolts, connectors, and circuit boards were all being pushed toward their breaking points by the environment. That context is critical when you look at odd shapes in the panoramas. Any anomaly you see could come from the outside world or from a camera, sensor, or transmitter that is being slowly ruined by heat and pressure. So now the tension is even sharper. You know Venus's surface is hot enough to melt common metals, under pressure like a deep ocean trench wrapped in supercritical CO2 with acid traces that attack most chemistry. You know any lander is on a strict death timer from the moment it arrives. Under those conditions, how did the Soviets ever get from early failures to landers that actually touched down, survived for an hour or more, and sent back the only photos we have from that inferno? How many times do you have to fail at a planet before you finally learn how to land on it alive? For the Soviet Union, the answer with Venus was a lot. The early Venera missions in the 1960s were more like target practice than clean landings. Some missed the planet, some lost contact on the way, some hit the atmosphere and never spoke again. Venera 3, which arrived in 1966, became the first human-made object to hit another planet's surface. But it was a dead impact. It plunged into Venus and sent back no data from the ground at all. It was a historic milestone and a scientific zero at the same time. Each one of those failures forced changes. Engineers saw where heat shields burned through, where parachute systems didn't deploy on time, where radios cut out too early. They thickened the protective shells. They redesigned the pressure vessels to take higher loads. They changed entry angles so the capsules didn't skip off the atmosphere or burn up too fast. Slowly, mission by mission, They built up a map of what Venus would tolerate and what it would instantly destroy. So when did smash into hell and die finally turn into land, barely survive and talk? That turning point came with the Venera 7 in 1970. This mission was designed specifically to try a true soft landing. The capsule hit the atmosphere, rode out the heating, deployed its parachute, and made it all the way down to the surface. The landing was rough. The signal was weak and partially lost. For a while, even the Soviets weren't sure it had worked. Later analysis showed that the lander did in fact touch down in one piece and transmit data from the surface for about 23 minutes. Those 23 minutes gave humanity the first direct measurements from the ground of another planet. The numbers were clear: pressures of many tens of bar and temperatures of hundreds of degrees Celsius. Not guesses, not models, but actual readings from a device sitting on the Venusian surface. It wasn't a full science lab. There were no panoramas, no drills, but it proved one crucial thing: you can design a capsule that survives descent, lands, and lives long enough to send back data through that atmosphere. Once you know you can touch the ground and say hello, the next question is obvious. Can you open your eyes and actually see the place? That step came with the mid-1970s missions, especially Venera 9 and Venera 10 in 1975. These landers carried cameras and were built on a more robust platform. They again slammed through the atmosphere, landed, and this time managed to send back black and white panoramic images from the surface. The photos were low resolution by today's standards, but they were historic, the first images ever taken from the surface of another planet other than the Moon. Those early panoramas showed blocky rocks, a flat horizon, and a hazy sky. They also proved that cameras, lenses, and scanning systems could function, at least briefly, in an environment at around 90 bar and more than 450 degrees Celsius. With that, the design target changed. It was no longer enough to just touch down. The goal became land safely and look around, measure the rocks and air in detail, and keep doing it for as long as the hardware can stand it. So how do you turn a rough early lander into the more advanced machines that eventually took the controversial photos? By the late 1970s, Soviet engineers had evolved the Venus lander design into a tough, compact, almost standardized system. The heart of it was a strong spherical pressure vessel, about a meter across, wrapped in layers of thermal insulation and protected on the outside by armor against impact and abrasion. Under that shell, they mounted hardware for parachutes and braking devices. Around the base, they added a crushable landing ring to soak up the final impact when the capsule hit the ground. The payload section became more complex and more capable. Rotating camera units were mounted low around the equator of the sphere, giving panoramic views in opposite directions. A drill assembly was installed to sample the surface material. Rock analysis instruments, gas analyzers, meteorological sensors, and in some missions, simple seismometer and microphone systems were packed into the limited internal volume. Everything had to be designed for quick operation, because every minute on the surface meant rising internal temperatures and ticking down to thermal death. This mature design led directly to the two missions at the center of the moving object story, Venera 13 and Venera 14. So what made those two landers different enough that their images are still being argued about today? Venera 13 and Venera 14 were launched in late 1981 as a pair. Each spacecraft had two main parts: an orbiter-style bus that stayed in space and relayed data, and a descent capsule carrying the lander. After cruising from Earth to Venus, each descent capsule separated and entered the atmosphere on its own trajectory. Venera 13's lander touched down on March 1st, 1982, Venera 14's on March 5th, 1982. Both landed on relatively flat basaltic plains in the region near Phoebe Reggio, but hundreds of kilometers apart, so they sampled different sites. The design lifetime for their landers was about 32 minutes on the surface. In practice, Venera 13 survived for about 127 minutes, almost 4 times that. Venera 14 lasted about 57 minutes, nearly double its planned life. During those extra minutes, they delivered a lot, multiple panoramic images, several rock chemistry measurements, profiles of temperature and pressure, wind data, and recordings of mechanical operations and ambient sounds. For Venus, these were long-duration landings. The cameras on these landers produced the first colour panoramas from the surface of another planet. They showed the orange-tinted landscape rock distributions and parts of the lander itself. Because the cameras scanned line by line and the lander repeated scans, scientists ended up with sequences of images covering the same ground at slightly different times. Those sequences, taken while the hardware was slowly degrading in extreme conditions, are exactly the data that would later be re-examined for signs of motion. But here's the key question that raises the stakes of everything in those frames. How many other landers from any nation have done this on Venus since then? As of 2026, the answer is none. The Soviet Venera program, up through Venera 13 and 14 and a few related missions, remains the only effort that has actually landed hardware, taken images, and returned surface data from Venus. Later missions by NASA and others, Pioneer Venus, Magellan, Venus Express, Akatsuki, have all stayed in orbit or operated only in the upper atmosphere. No one has sent a new lander to the surface and survived there since the Soviet era. That makes every Venera image and every glitch or odd shape in those images uniquely important. There is no modern, higher resolution, cleaner dataset to compare to. If there's even a hint that something in those panoramas moved between scans, that hint is locked in hardware and software from the early 1980s. No spacecraft has gone back to rephotograph the same sites with better cameras. So now the question tightens. The Soviets finally mastered getting to the surface and staying alive long enough to take panoramas. Those panoramas later sparked claims of motion. But before you can judge those claims, you need to know what the landers were actually like on the inside. How do you pack cameras, drills and sensors into a 1-meter metal shell that you know will be cooked and crushed in under 2 hours? And what does that do to the reliability of every single pixel you see? How do you design a machine you know is going to die in under 2 hours and still trust what it shows you from the most hostile surface in the solar system? Start with the shell. The Venera 13 and 14 landers are basically metal spheres about 1 meter across, a bit over 3 feet. That shape is not for looks, it is the best way to spread crushing force evenly. The pressure at the surface of Venus is around 9 megapascals, roughly 92 to 93 times Earth sea level pressure, about 1,300 pounds per square inch. The hull has to survive that from the outside while keeping the inside close to normal room conditions for as long as possible. Inside the sphere, there is a smaller, thermally controlled compartment where the electronics live. It starts out near 20 degrees Celsius, around 68 Fahrenheit. The designers know that as soon as the lander hits the lower atmosphere, heat will start to leak in through the metal shell and any structural supports. They can't fight the pressure, they accept it. What they can control for a short time is the temperature inside. That leads to the next problem. How do you cool something when outside is hotter than your oven at home? On Earth, spacecraft and satellites get rid of heat by radiating it into cold space. On Venus's surface, there is no cold to radiate to. The air around the lander is at 460 to 470 degrees Celsius, 860 to 880 Fahrenheit. Radiators would only bring more heat in. So the Venera landers flip the idea. They don't try to dump heat, they try to absorb it. They pack the interior with thermal mass and phase change materials. Think of blocks of special substances that stay solid up to a certain temperature and then start to melt. While they melt, they soak up a lot of energy without jumping in temperature as fast. That gives you a short window where the electronics can stay under their maximum temperature, even though the outside shell is baking. Engineers ran models that showed how fast heat would conduct through the metal hull and into the core. Even with insulation and these heat-absorbing materials, the calculation said you get roughly 30 minutes before key components hit their limit. That is why the official design life was only about half an hour. When Venera 13 lasted about 127 minutes on the ground, it didn't mean the physics was wrong, it meant The design had margins, the materials performed better than the worst-case assumptions, and the system simply took longer to cross the failure line. But that extra time came with a cost. The longer it survived, the hotter the internals became, and the more stressed every part of the lander was. Now look at what they chose to cram into that tiny, short-lived space. Inside the pressure vessel, they had to fit 2 television camera systems, power electronics, radio transmitters and receivers, batteries, a drill mechanism, a sample handling system, gas analyzers, a rock chemistry instrument, and sensors for pressure, temperature, and wind. There was also a combined microphone and simple seismometer package called Groza 2, designed to pick up both acoustic vibrations and slow ground motions. The drill was small but important. It extended down from the bottom of the lander and bored roughly 3 centimeters, a little over an inch, into the rock. It then pulled up about a cubic centimeter of material, roughly the size of a sugar cube, and moved it into an X-ray fluorescent spectrometer. That instrument hit the sample with X-rays and measured the energy of the re-emitted photons. From that spectrum, scientists could tell what elements were present and in what ratios. That is how we know the Venera 13 and 14 landing sites sat on basaltic volcanic crust, similar in some ways to Earth's volcanic plains. Gas analyzers took in small volumes of the surrounding atmosphere, measured its composition, and fed that data to the radio system. Meteorological sensors tracked changes in pressure, temperature, and wind speed just above the surface. All of this was happening in parallel under brutal conditions, with no chance for repair if anything jammed. But the most famous part of the payload, and the part that later caused all the debate, was the camera system. Each lander had 2 scanning cameras mounted low on the hull, roughly opposite each other. You can think of them as sideways-looking eyes close to the ground. Before landing, those cameras were protected by lens caps, because dust, debris, and heating during descent could easily scratch or coat the optics. Right after touchdown, small explosive charges fired to blow those protective caps clear of the field of view. Once the caps were gone, the cameras got to work. They did not take a full frame in one instant. Instead, each camera scanned horizontally, building the panorama line by line as a mirror or optical element rotated. It took minutes to complete a full sweep of about 180 degrees or more. The brightness values for each narrow strip were sent back to Earth as data, where ground teams reconstructed them into the curved panoramas you've seen. Because the cameras scanned over this time, not all parts of the image are from the same exact moment. The left side of the panorama might represent the scene at, say, 1 minute after landing, while the right side could be closer to 3 or 4 minutes. When the lander repeated the scan, the second panorama would start at a later time. That means if anything in the scene changed between those periods, whether it was a shadow dust, a small piece of hardware settling, or even an instrument glitch, it could show up as a difference between panoramas. Those differences are exactly what later investigators, like Ksanfomaliti, stared at. If a small bright patch appears near the lander in one panorama and seems to be shifted or missing in the next, the natural question is, did something move, or did the camera system, already under thermal stress, distort or misrecord that part of the image? All of this was happening inside a machine that had no long-term future by design. Nothing on Venera 13 or 14 was built to last days. The metals in the structure were slowly creeping under constant pressure. Solder joints and connectors were heating far beyond safe margins. Lubricants in moving parts like the drill and camera scanners were changing viscosity, possibly thinning or breaking down. Electronics were being pushed toward their maximum rated temperatures and then beyond. Mission planners knew this. The mission architecture assumed total failure within a few hours, maximum. The idea was not, we might make it and do a long mission. The idea was, we will die fast. So do as much science as possible before that happens. That mindset matters when you interpret every anomaly. A strange bright spot near the lander could be hardware, a rock, or a lens cap. A shape that seems to walk between panoramas could be a real object in the scene, or it could be the signature of a component drifting out of alignment as it heats, or a data glitch in a radio link that's being slowly degraded by conditions. So now you have the full setup. A 1 meter pressure sphere pushed to its limits, cooled only by sacrificial materials, packed with instruments running on a strict thermal deadline, and cameras that scan slowly while the entire system is being roasted. In that context, if you see something in the images that wasn't there before, are you really looking at a living thing on Venus, or just watching a dying robot's vision distort in real time? How do you actually drop a spacecraft into an atmosphere that can crush a submarine and still get useful data back before everything fails? In March 1982, the answer played out twice, almost like a repeat experiment. First with Venera 13, then with Venera 14. On March 1st, 1982, the Venera 13 descent capsule separates from its cruise bus and lines up for entry. A few days later, on March 5th, Venera 14 does the same. Both capsules hit the top of Venus's atmosphere at more than 11 kilometers per second over 25,000 miles per hour. At that speed, even thin air slams into the heat shield like a wall. Temperature at the shield surface shoots up to thousands of degrees. The material doesn't just get hot, it burns away on purpose layer by layer, carrying heat with it. That's the ablative shield doing its job. As the capsules sink deeper, deceleration climbs. You're looking at multiple G of braking as drag builds up. Instruments inside are recording how fast the capsules are slowing down, how pressure is rising, how temperature is climbing. High up, the atmosphere is still roughly normal gas. As they fall, pressure increases smoothly, but by the time they're near the surface, the air is so dense and hot that it behaves like a supercritical fluid. It's not a simple gas anymore. The descent profiles Venera 13 and 14 send back help pin down exactly where that transition region is. At a certain altitude, each capsule deploys a parachute. That slows the fall when the air is still relatively thin, but Venus's lower atmosphere is so thick that if you kept the parachute all the way down, you'd barely move, and the lander would waste its short life hanging in the sky heating up. So deeper in, once drag from the air alone is enough, the system cuts the parachute loose. From that point, the capsule descends on aerodynamic drag only, essentially falling through a hot, heavy fluid until its crushable structure hits the ground. Touchdown for Venera 13 is just east of Phoebe Reggio. Venera 14 lands a few hundred kilometers away, still in a region of flat plains. In both cases, the accelerometers register a sharp spike as the lander hits, then a quick decay as the crushable ring under the base deforms and absorbs energy. The pressure vessel inside stays intact. That one moment is the difference between another impact and die mission and the surface data that still drives arguments today. What do those landing sites actually look like once the cameras come online and the rock instruments start running? From the reconstructed panoramas, both locations are low-relief, blocky plains. You see scattered rocks, some angular, some more rounded, sitting on a relatively firm surface. There's no deep dust swallowing the lander, no obvious steep slopes or boulders taller than the probe. The X-ray fluorescence spectrometer on each lander analyzes drill samples and returns element ratios that match basaltic rocks. In detail, they line up with things like alkali or lucite basalts on Earth. That tells you you're standing on a volcanic surface formed from lava flows, not on weird exotic ices or metals. Those chemistry measurements, combined with radar maps from orbit, support the idea that much of Venus has been resurfaced by massive episodes of volcanism. Large parts of the crust have been paved over by lava, erasing older terrains and craters. These spots where Venera 13 and 14 land are typical examples of those plains, not rare or special sites. The landers also do something no one had done on another planet before. They send back real in situ sound from the surface. Venera 13's Groza 2 instrument includes a microphone. Once on the ground, it picks up the impact sounds as the lander hits, the sharp noises of pyrotechnic devices firing, the whirring and clacking of mechanisms like the drill and camera scanner, and a steady low-frequency background from the wind. From the character and level of that wind noise, combined with pressure sensors, scientists estimate surface winds of a few meters per second, maybe up to around 10 miles per hour. That doesn't sound like much, But in air about 90 times denser than Earth's, those slow winds carry a lot of kinetic energy. They can push on rocks, dust, and lander parts more strongly than you might expect. Along with audio, both landers carry a simple vertical axis seismometer as part of the same Groza 2 package. It's not a full seismology station, but it can respond to vibrations transmitted through the ground. Venera 13, during its 127 minutes of life, doesn't record any clean, obvious seismic events that stand out from the noise. Venera 14, during its shorter 57-minute run, records a couple of small signals that some researchers later flag as possible microseisms, tiny Venus quakes, or maybe distant tectonic activity. The problem is that at that sensitivity level, it's hard to separate ground motion from everything else: wind buffeting, internal lander movements, mechanical operations. The data are interesting but not decisive. They at least suggest that Venus might not be completely seismically dead, but they don't give you a clear, dramatic quake. All of this, entry data, landing impact, rock chemistry, wind, maybe a hint of seismic noise, is coming in under one constant constraint: time. From the instant each lander hits the surface, a countdown starts. Set not by a clock, but by physics. Heat is leaking in. Phase change blocks are absorbing it but slowly saturating. Internal temperatures are rising degree by degree. Venera 13 runs for about 127 minutes. During that time, it sends multiple panoramas from both cameras, several rock analyses and detailed pressure and temperature logs. Venera 14 runs for about 57 minutes, shorter but still long enough to capture black and white panoramas, rock chemistry, and environmental data. Each panorama scan takes minutes. Between scans, other instruments are working, and the lander is heating up further. Because the cameras operate in sequences, you end up with sets of images that cover roughly the same terrain, with time gaps in between. That is where the later controversy is born. When you put those panoramas side by side and look closely, you notice that some small features in the foreground seem to appear, change, or disappear between frames. Under normal conditions, that might be easy to attribute to lighting changes or minor alignment shifts. But here, you're looking at a world where wind is strong in terms of force, the camera system is scanning line by line, and the entire lander is slowly deforming and heating near its failure point. Every extra minute the lander stays alive gives you more data, and more chances for tiny shifts, glitches, or hardware movements to show up in the images. By the time internal temperatures are well above their design targets, you can't expect the system to behave perfectly. Connectors expand, supports flex, timing drifts. Yet the cameras are still trying to produce clean panoramas and send them through a harsh, noisy radio path back to Earth. That's the situation you have to keep in mind when 30 years later, someone circles a small bright or dark patch in those panoramas and says, "This wasn't here before, now it is, now it's gone." The claim of something moving on Venus doesn't come from a clear video of an object walking. It comes from tiny differences between time-staggered scans made by a lander that was in the process of cooking itself to death while staring at a basalt plain. So the tension now is this. The March 1982 descents gave us our only direct look and listen from Venus's surface, but they also gave us a messy, time-smeared data set from machines under extreme stress. When you see a shapeshift between those scans, are you looking at the planet doing something unexpected? Or are you just seeing how an overheated, overpressured camera and radio system break down under conditions no lab on Earth can fully reproduce? How much can you trust a picture when it isn't really a single picture at all, but a time slice smeared across a landscape by a machine that's dying as it looks? Start with the basic fact. The Venera cameras did not take snapshots. Each camera built an image by scanning the terrain line by line. A rotating mirror or turret swept across the horizon, and as it moved, the detector recorded brightness for a narrow strip. Then it stepped to the next strip and the next. One panorama took tens of seconds to a couple of minutes to assemble. That means a frame from Venera 13 or 14 is not an instant frozen in time like a modern phone photo. The left edge of the panorama could have been captured at say 10:05, while the right edge might be 10:06:30. If anything changes in the scene during that period, lighting, dust, hardware position, or if the camera timing shifts or jitters, that change shows up as a distortion or as an apparent motion inside a still image. Now, add on top that the lander is heating up, materials are expanding, and the scan mechanism is a moving part under extreme stress. Any tiny slippage in scan speed, any hiccup in the encoder that tells the system you are here, can bend lines, stretch features, or make small objects look shifted between passes. When later investigators put two panoramas side by side and look for differences, some of what they're seeing is not the planet changing. It's the camera and its clock slowly drifting under brutal conditions. So even before you talk about creatures or objects, you're dealing with images that are stitched together in time, not snapped in an instant. That's your first warning sign. Apparent motion in a scanned image is a lot easier to fake by accident than motion in a true instantaneous photo. Then there are the lens caps, which turned into unintentional actors in this story. Right after landing, the landers fire explosive bolts to get rid of dust covers and lens caps in front of the cameras. Those caps are small, bright pieces of hardware that land somewhere near the base of the probe. We know what they look like from the engineering drawings and pre-flight tests. They're roundish, high-contrast objects, exactly the kind of thing that stands out in a low-resolution panorama. When Leonid Ksanfomaliti published his 2012 analysis, one of his main examples was a bright disk that appears near the lander in one image and seems to be in a slightly different spot in another. He treated that as one object that had moved. Later, people who knew the hardware, including Venera engineers and NASA image specialists, went back to the geometry. They pointed out something simple but crucial. Each lander ejected two lens caps, one for each camera. The small, bright shapes in the panoramas match the size and reflectivity of those caps. When you reconstruct where the cameras are, where the caps would fall, and how each camera's field of view overlaps, a clean explanation appears. The disk isn't a single thing travelling across the ground. It's two nearly identical caps in two different positions, seen by different cameras at different times. In other words, hardware, not biology. A known part exactly where you'd expect it, recorded by an imaging system that sees from slightly different angles. That alone is enough to turn one of the strongest moving candidates into a simple engineering artifact. But that's still not the whole problem. The images Ksanfomaliti worked with in 2012 were not raw original data fresh from the lander. They were the result of decades of copying and processing. Think about what happened between 1982 and 2012. The original data came down as analog or low bitrate digital signals. Those were decoded, turned into images, and often printed. Later, people scanned those prints. They stretched contrast to make faint details easier to see. They sharpened edges. They reprojected the original curved panoramas into flatter views so they look better on a page or a screen. Sometimes they interpolated across missing or noisy lines so the image wouldn't have obvious stripes. Each of those steps can add artifacts. Sharpening can turn a gentle gradient into a fake edge. Interpolation can invent texture where there was none. Noise, which is not just random grey but has patterns, can be amplified until it looks like structure. By the time you get to a heavily processed second or third generation digital copy, you're often looking at the original scene plus a lot of software decisions layered on top. Planetary Society analysts and others went back and compared different versions of the same Venera frames. High-quality, minimally processed copies versus the contrast-boosted, sharpened ones that Ksanfomaliti used. They found that some of the shapes he labelled scorpion and black flap only look distinct in the heavily enhanced versions. In cleaner data, those regions either look like ordinary rocks and noise, or the supposed shapes blur into the background. That's a red flag. If a creature disappears when you back off the processing, you're probably chasing an artifact, not anatomy. There's another geometric effect that makes this even trickier. Parallax. The Venera cameras sit close to the ground. That means that nearby objects, even just tens of centimeters, maybe a foot or two away, show very strong shifts against the background when the viewpoint moves slightly. If the camera scanner or turret flexes by a few millimeters, or the lander settles just a bit into the soil, or the exact starting angle of one scan is off by a fraction of a degree, the apparent position of a rock or lens cap in the panorama can change. Between two panoramas taken a few minutes apart, you might have tiny mechanical changes and slightly different registration. Unless you carefully align the images using fixed, distant features, close-up objects will seem to drift. That drift can look like a small rock or bright object creeping along the ground, when in reality everything is stationary and only the viewpoint has shifted a little. This is why serious imagery analysis involves registering frames to sub-pixel accuracy, not just eyeballing them. Without that, parallax and perspective tricks can easily fake motion. And on Venera, with the cameras mounted low and the environment actively pushing on the lander, parallax is not a minor effect, it's baked into the geometry. On top of all that, remember how these images got home? Through a long, noisy communications path from a lander sitting in a super hot, super dense atmosphere. The data link from the lander up to the bus, and from the bus back to Earth, had tight bandwidth limits. The signal had to pass through a thick, refracting atmosphere, then cross tens of millions of kilometers of space. A lot can go wrong along that path. You can get dropouts, where some bits never arrive. You can get bit flips, where a 0 turns into a 1 or vice versa because of noise. You can get timing errors, where the system misreads where one line ends and the next begins. In a picture built line by line, a short dropout might show up as a horizontal streak or a patch of wrong brightness. A timing hiccup might shift a chunk of the image sideways. On very low resolution data, a small cluster of corrupted pixels can take on a shape that your brain wants to interpret as something familiar, an outline, a limb, a body, especially if someone draws a contour around it and gives it a name like scorpion. The hard part, and the core of the whole controversy, is deciding which anomalies are just that, glitches in a stressed camera and a noisy radio link, and which, if any, correspond to actual things sitting on the ground next to the lander. Every time you circle a blob and say this moved, you have to rule out scan timing shifts, thermal flexing, parallax, processing artifacts, and transmission noise. So when someone points to a grainy shape in these panoramas and claims it is crawling across the Venusian surface, they're doing it on top of a very unstable stack of image steps, scanned over time, from a flexing platform, through a failing electronic system, transmitted over a noisy link, processed and reprocessed for decades. That doesn't mean every anomaly is fake, but it does mean the bar for calling something real motion has to be extremely high. Given all that, what exactly did Ksanfomaliti see in these messy images that convinced him it was still worth talking about possible life on the surface, and how did the rest of the scientific community respond? In 2012, a Russian planetary scientist pulls a 30-year-old dataset off the shelf and basically says, everyone missed something. That scientist is Leonid Ksanfomaliti, and the old data are the Venera 13 and 14 panoramas you've been hearing about. Most people saw those images once, decades ago, as proof that the USSR actually landed on Venus. Ksanfomaliti looks at them again with a different question in mind. Do any small features change between scans in a way that looks like real motion? He takes sequences of panoramas from the same lander, same camera, same approximate field of view, but separated by minutes. Then he goes into the details. He marks small, bright and dark patches near the lander on one panorama, then scans for them in the next, where earlier work focused on the broad scene, rocks, horizon, sky. He focuses on the little stuff within a couple of meters of the probe's base. Based on the camera geometry, the known height of the camera above the ground, the spacing of rocks in the scene, he estimates the actual sizes of these patches. He comes up with numbers on the order of 10 to 50 centimeters, about 4 to 20 inches. So these are not tiny specks at the limit of resolution. In his view, they are big enough that, if you were standing there, they'd be obvious chunks of something on the ground. Then he lines up timestamps from the radio data with the scan timing. When he sees a feature that is present in one panorama, apparently shifted or absent in another, and then maybe back again, he argues that this behaviour is better explained by some form of slow motion on the surface than by random noise. That's his basic move: consistent changes over tens of minutes in objects tens of centimetres across, right next to a lander in a supposedly dead environment. One of his favourite examples is what he names the disk. On one Venera 13 panorama, he points to a bright, roughly circular patch near the lander. It stands out against the darker rocks and ground. On a later panorama from the same camera, he identifies what he says is that same patch, but now it seems shifted slightly in position relative to nearby features. The time between the two scans is on the order of tens of minutes, not seconds. Ksanfomaliti's argument is straightforward. This can't be just dust blowing by, because dust at that scale would not show up as a sharp, bright object with clear edges. It also seems too coherent over time to be just a glitch. It appears as a distinct object in both images, not as random speckling. To him, the simplest explanation is that a discrete object, about tens of centimetres across, has moved a small distance across the surface. He doesn't claim it sprinted across the frame. The implied crawl is slow, maybe a few centimetres over that interval. But slow movement is still movement. In a place like Venus's surface, even a short, careful shuffle by a 20 or 30 centimetre object would be a huge deal. Then there is what he calls the black flap. Here he focuses on a dark patch near the lander that changes shape and contrast between images. In one panorama, it's lower contrast and closer to the ground. In the next, it looks darker and appears slightly lifted or tilted. Ksanfomaliti suggests that this could be a flexible structure, some kind of flap or appendage that rises and falls over time. When it lifts, it would cast a deeper shadow or present a different angle to the camera, making it look darker and slightly shifted. When it drops, it blends back toward the background. He ties these brightness swings to the scan timestamps, arguing that the changes line up with realistic time intervals for slow physical movement, not with random line-by-line noise. In his view, ordinary noise would be uncorrelated from one scan to the next and would not produce such a specific pattern in the same location across multiple panoramas. And then comes the claim that really grabs attention: the scorpion. In at least one processed Venera 13 frame, Ksanfomaliti highlights an elongated shape that he says looks like a scorpion-like form. He describes it as having a central body with several outgrowths or legs extending from it. It is not sharp, it's a fuzzy, low-resolution blob, but with enough enhancement and contouring it can be interpreted as a segmented body with appendages. Using the same geometric reasoning, camera height, field of view, distance to features, he estimates the length of this shape at about 40 centimetres, roughly 16 inches. That's not a microbe, that's a macroscopic creature-sized object, at least in outline, sitting in front of a lander on a surface hotter than a typical industrial furnace. He also claims that something similar might be visible in the Venera 14 imagery, though the match there is weaker. The idea is that both landers may have captured the same general type of object, some unknown surface life form, at two different sites. Now put the numbers together. If that scorpion shape were real and alive, then you're talking about an organism roughly the size of a house cat's body, existing at about 460 degrees Celsius and around 90 bar, in an atmosphere of supercritical CO2 with traces of sulfuric compounds. That is far beyond the operating window of any Earth biology we know, even in short bursts. It would demand completely different biochemistry, structural materials, and information storage. That is exactly why the claim sounds extreme and why it draws attention. To his credit, Ksanfomaliti does not go full sensationalist in the actual paper. His language is cautious and technical. He calls these objects with possible terramorphic features, meaning their shapes remind him of familiar Earth forms. He talks about manifestations of possible life activity and proposes that these patterns should be studied more deeply. He doesn't write aliens on Venus in big letters. He frames his work as a hypothesis. If these changes cannot be explained by known instrumental or environmental effects, maybe they are due to life. But once the paper is out, it leaves the relatively slow world of journals and lands in the fast world of headlines. Popular media sees Venus, moving objects, possible life, and Soviet landers in the same story and runs with the most explosive version. Articles and posts pop up with titles along the lines of "Soviet probe photographed living creatures on Venus," and "Did we miss life in old Soviet images?" Most readers don't see the hedged language. They see the images with circles and labels, disk, flap, scorpion, and a one-line summary. Online, the visuals spread even faster. Cropped, contrast-boosted versions of the panoramas circulate with arrows pointing at blurry shapes. People repost them, recompress them, add their own color tweaks, and the artifacts get stronger or stranger each time. The original context, scan geometry, lens caps, transmission noise, thermal stress, mostly disappears in the repost chain. What's left is a powerful idea. NASA said Venus was dead, but these forgotten Soviet photos show something crawling down there. So you end up with a perfect storm. Old, hard-to-interpret data, new image processing tools in the hands of both professionals and amateurs. A planet with a well-earned reputation as a hellscape which makes any hint of life there seem shocking, and a deep human tendency to see patterns and living forms in noisy images. At the centre of that storm is a simple question: are these disk, black flap, and scorpion features real objects doing something on Venus? Or are they just the complicated byproducts of hardware and data pipelines pushed to the edge? To answer that, you need one more piece: the response from the people who built and analysed these images in the first place. The engineers and mission specialists who looked at the same data and saw something much less exotic than alien life. When the 2012 Moving Objects paper comes out, the first big pushback doesn't come from people shouting, "That's impossible." It comes from people who know this hardware inside out saying, "We've seen that shape before." Engineers who worked with Venera-type landers, plus NASA image specialists, look at the bright disk Ksanfomaliti highlights and recognize it immediately. The Venera 13 lander ejects 2 lens caps when it reaches the surface, one for each camera. Those caps are small, bright, and circular in outline. They were designed to blow off and land somewhere near the base of the lander. So these engineers go back to the basics: drawings, photos of the lander before launch, and the known geometry of the cameras. They reconstruct where the cameras sit, what their fields of view cover, and where caps would likely fall if fired off at specific angles. When they overlay that on the panoramas, the bright disk positions line up very well with where you would expect those caps to end up. In other words, the frames are not catching an unknown thing, they're catching pieces of the lander itself. Then they point out something simple that flips the whole disk argument around. Ksanfomaliti treats the bright feature in one panorama and the bright feature in another as the same object that has changed position. But each Venera lander had 2 caps, not one. That opens a different explanation. You're not looking at before and after shots of a single disk that has moved. You're looking at 2 different caps lying in 2 different spots, each seen by a camera at a slightly different angle and time. From that point of view, there is no motion to explain. You have 2 static pieces of hardware on the ground, each captured in 1 or more scans. The shift in apparent position comes from camera viewpoint and scan timing, not from anything crawling. That hardware-based explanation fits the engineering, the geometry, and the brightness and size of the objects, without needing any new biology. So what happens to the scorpion under the same kind of scrutiny? Independent analysts dig for the best available versions of the original Venera frames. They find copies closer to the raw data with less aggressive contrast stretching and less sharpening. Then they compare those to the highly processed images used in the 2012 paper, where the scorpion outline looks the most convincing. In the cleaner images, the area where the scorpion is supposed to be looks like a mix of rocks and noise. The clear body plus legs pattern is muted or not visible at all. The more you back off the processing, less sharpening, less interpolation, more faithful reproduction of the original line structure, the less that shape stands out. It starts to blend into the same low-contrast clutter that fills the rest of the frame. NASA image people and other critics make a straightforward point. If a supposed object only appears when you push the processing hard and it fades or vanishes in more original data, then it's much more likely to be an artifact of enhancement than a real thing. Sharpening and interpolation are good at turning random noise into fake edges and fake structures. They are not neutral. They make your brain want to see outlines where none exist. So the disk can be handled as hardware. The scorpion looks like processing and noise. What about the idea that something big enough to see might have actually moved around the lander? Do the other instruments back that up in any way? That's where cross-checks matter. If you think a real 40-centimetre object about 16 inches long walked or shuffled around the lander on rock, several things could happen. The seismometer might register small impact or vibrations as it steps. The microphone might pick up extra scrapes or thumps not tied to known mechanisms. The cameras might see dust being stirred up or changes in reflectivity along a path. You might even see slight changes in how nearby rocks are shadowed if something large passes by. But when you look at the actual Venera 13 and 14 records, you don't see a clear match. Venera 13's seismometer log is quiet in terms of local distinct events. Venera 14 has a couple of possible micro-seisms, but our timing doesn't line up cleanly with any claimed motion in the images, and that they're easily explained by wind or internal lander activity. Changes in brightness in the panoramas usually match known operations. The drill has been used, a cap has fallen, or the scan started at a slightly different time. There is no extra class of unexplained signals that scream, something heavy moved nearby. In a setup this limited, you'd never expect a perfect audio-video seismic match. But the absence of any clean, repeatable pattern that lines up with the supposed creature activity works against the idea of a macroscopic, active life form pacing around the lander. Given how crude the sensors are, the least you'd expect is some odd spike in one of the other channels that doesn't correlate with known hardware events. You don't see that. Even with that strong pushback, the story doesn't just stop. In the 2020s, a few small groups revisit the same Scorpion region with newer tools. Machine learning, pattern analysis, fractal comparisons. They run shape recognition algorithms over the frames to see whether the outline of the Scorpion patch is statistically different from the shapes of surrounding rocks or from known artifacts. Some of these studies claim there is a measurable difference, and they float the idea that a biological interpretation can't be totally ruled out. But when you read the fine print, even those authors admit something important. The data quality is low, the resolution is poor, the processing history is messy. Any pattern they're detecting might just as easily be born from the way the image was enhanced as from something on the ground. They usually conclude that the probability of a real organism is low, and that a non-biological explanation remains more likely. Meanwhile, the mainstream planetary science view stays steady. Most experts accept the lens cap explanation for the bright disk. They see the black flap and scorpion as combinations of noise, enhancement artifacts, and perspective effects in a harsh environment. They put the whole episode in the same category as other famous misidentifications. The face on Mars, odd bunnies caught by Mars rovers that turned out to be bits of insulation, and so on. Interesting as a cautionary tale, but not evidence of alien life. So you end up with a split. On one side, a solid hardware-based case that the strongest moving object is just a lens cap and that the rest of the shapes collapse under cleaner analysis. On the other, a small but loud group that says, we can't be 100% sure, and the shapes are weird enough that maybe, just maybe, something exotic is going on. That brings you to the real deeper problem. Given what you now know about Venus's surface and these landers, how realistic is it, on pure physics and chemistry grounds, that anything even vaguely like a 40-centimetre organism could survive, move, and stay functional down there in the first place? If you strip away the blurry photos and the headlines, one hard question is left. Does the basic physics and chemistry of Venus's surface even leave a crack open for anything to stay alive, in any form we'd recognise as life? Start with thermodynamics. At the surface, you're at around 735 Kelvin, roughly 460 degrees Celsius, about 860 degrees Fahrenheit, and about 92 bar of pressure. That is not just very hot. That is the regime where many reactions that break complex molecules apart run incredibly fast. A rough rule of thumb in chemistry is, for many reactions, rates go up by about a factor of 2 for every 10 degrees Celsius increase. It's not exact, but it gives you a feel. Take a process that already happens at room temperature, say around 30 degrees Celsius, and now push it more than 400 degrees higher. That's over 40 of those 10-degree steps. Doubling 40 times is not a small increase. You jump by many orders of magnitude. Reactions that would take years or hours on Earth can happen in fractions of a second or a few seconds at Venus surface temperatures. Now apply that to the stuff Earth life is made of: lipid membranes, proteins, DNA or RNA. The chemical bonds that hold them together just are not designed for that heat. At 460 degrees Celsius, long chains start to break fast. Side groups fall off. Membranes lose structural integrity. Any delicate three-dimensional fold that a protein needs to work would be destroyed almost instantly. So even if you dropped a tough microbe from Earth onto Venus, its biomolecules would be shredded on the timescales of seconds to minutes, not days. So maybe you say, sure, Earth life can't handle it. But what about the toughest extremophiles we know? Don't they hang out in boiling vents and acid? On Earth, the record-holding hyperthermophiles, microbes that love heat, live in places like deep-sea hydrothermal vents and some hot springs. Their upper temperature limits sit around 120 to 130 degrees Celsius, roughly 250 to 270 degrees Fahrenheit. And that's under special conditions, often with high pressure and protective mineral surroundings. Go much higher, and their proteins denature, their membranes fail, and their DNA can't stay intact. In the lab, you can briefly push some biomolecules a bit higher if they're protected, but nothing we know of runs a living metabolism with replication and repair at hundreds of degrees Celsius. Jumping from 120 to 130 degrees to 460 degrees Celsius isn't a small extension, it's a whole different ballpark. You're not tweaking Earth biochemistry, you're basically throwing it out and inventing a new kind of chemistry from scratch. So could the pressure help? After all, high pressure can sometimes stabilize structures and raise boiling points. On Venus, that argument backfires. The 92 bar atmosphere is mostly carbon dioxide. At those pressures and temperatures, the CO2 near the surface behaves like a supercritical fluid. That means it's dense like a liquid, but fills space like a gas. It can dissolve and carry reactive species very efficiently. For a hypothetical organism, that means the environment is not only hot, it's also a powerful, penetrating solvent that can drive oxidizing reactions and other breakdown processes quickly into any exposed material. High pressure might keep some compounds from boiling away, but it also forces aggressive molecules right up against every surface and into every pore. So now your imaginary life form has to handle extreme heat, extreme pressure, and a chemically harsh supercritical CO2 medium all at once. That's a triple challenge, and none of those parameters are kind. The only way around that is to move beyond carbon-water life as we know it. Could you, in principle, design or imagine a life system built on something like high-temperature ceramics, metallic bonds, or silicon-based networks that stay solid and reactive at 700 Kelvin and above? People have written papers along those lines. They talk about silicon-oxygen frameworks, metal oxide clusters, mineral surfaces that shuttle electrons, and other exotic ideas. You can imagine metabolisms that are more like slow redox reactions across crystals than like cellular chemistry. You could picture information being stored in defects in a lattice or in layered mineral patterns instead of in DNA strands. On paper, nothing in physics absolutely forbids weird high-temperature systems that evolve and self-organize. But here's the key. Right now, these are thought experiments, not working models. We have zero experimental evidence of such systems actually doing what life has to do. Store information robustly, copy that information with variation, and undergo Darwinian evolution over long times. No one has built a tiny ceramic or metallic network that grows, divides, and evolves in a lab at 400 to 700 degrees Celsius. And even at those temperatures, you're still below Venus's surface regime. So yes, exotic biochemistry is possible in the loose sense that physics doesn't forbid it. But it's not something we can seriously plug into our data and say, this explains that blob in a Venera photo. We're in the realm of speculative fiction, not tested science. Then there's the timing problem that almost everyone overlooking these images forgets. How fast would such life move even if it existed? Imagine, for the sake of argument, that Venus has some kind of ultra-robust surface life with very slow metabolism. Maybe it takes hours or days to do what a microbe on Earth does in minutes. At such high temperatures, you might think everything speeds up. But if life has to fight constant breakdown, it might end up operating in a weird, slow, self-protective mode. You could picture organisms that grow or shift position on timescales of months or years, not minutes. Now compare that with Venera 13 and 14. Venera 13 survived for 127 minutes, Venera 14 for 57 minutes. That's your entire observation window, about 2 hours maximum. To clearly see a macroscopic object, maybe 40 centimeters long, move in that short time, the motion can't be glacial. It has to be fast and obvious on that scale. It has to cover a noticeable fraction of its own body length in under 2 hours, and do it in an environment where chemistry is trying to tear it apart. If you assume extremely slow, crystal-like life, 1 step per year or decade, your chances of catching it mid-move during a 127-minute snapshot are basically zero. To make the Venera moving object claims work, you need an organism that's active and mobile on human timescales while operating at 460 degrees Celsius in dense CO2. That's asking for the worst of both worlds: high-speed behavior in a regime where even stable structure is already a huge stretch. Put all that together, and you see why most scientists set the bar so high. It's not that they refuse to consider life in extreme places. They already do that with subsurface Mars, ocean worlds like Europa, and even Venus's own clouds. It's that Venus's surface, at around 735 Kelvin and 92 bar, is so far outside the known envelope that any claim of active macroscopic life there has to clear an enormous hurdle of evidence. Blurry shapes in line-scanned images from a dying 1980s lander do not clear that hurdle. Not when thermodynamics, known biology, and basic chemistry all lean hard in the other direction. But here's the twist: just because the surface looks like a dead end for life, that doesn't mean the entire planet is off the table. There is one region above that hellish ground where temperature and pressure actually fall back into the maybe zone for life, if you can tolerate acid and live in the air. And that's where the Venus life debate has now moved. So if the surface is almost certainly a chemical killing zone, what about higher up in the clouds, where Venus suddenly starts to look disturbingly like a strange, hot version of Earth's own atmosphere? If the surface of Venus is almost certainly lethal to life as we know it, why are serious scientists still arguing about life on Venus at all? Because higher up, the planet changes character completely. Go up to about 50 to 60 kilometers altitude, roughly 30 to 37 miles above the surface. Here, the temperature drops into a range you recognize, around 20 to 60 degrees Celsius, about 68 to 140 degrees Fahrenheit. The pressure is between about 0.5 and 2 bar, so between half and twice Earth sea level pressure. If you only looked at those two numbers, temperature and pressure, this layer of the Venusian atmosphere suddenly looks a lot like the lower atmosphere on Earth. This is exactly where some probes have flown through and sampled the air directly, measuring gases and the tiny particles that form the clouds. Modern climate models that simulate Venus's atmosphere also point to this band as a region where liquid droplets can exist and where the water activity, basically how available water is for chemistry, occasionally gets close to what some extremophile microbes on Earth can tolerate. It's still not comfortable, but it's no longer totally off the chart. So if there is any place on Venus where life could function, this is the first candidate. Not on the rocks, but floating in the sky. Then comes the catch, and it's a big one. those droplets are not water clouds. They are mainly concentrated sulfuric acid, H2SO4, with only small amounts of water and other solutes mixed in. On Earth, a handful of microorganisms can handle very acidic environments with pH values near zero. They live in acid mine drainage, volcanic pools and other nasty places, but even they don't live in almost pure sulfuric acid. They need some buffering, some way to keep internal chemistry away from direct, constant acid attack. For cloud life on Venus to work, you'd need tricks. One idea is that life wouldn't be spread evenly through every drop, but would live in microenvironments, tiny pockets inside droplets where the chemistry is a bit less harsh. Another is that gases like ammonia, NH3, could act as buffers, neutralizing some of the acid locally and raising pH inside microdroplets. Complex organic molecules could also help by forming protective shells or membranes that resist acid, the way some Earth microbes use special lipids to survive in extreme conditions. There have been claims of tentative detections of ammonia in Venus's clouds from spectroscopic data. Some researchers argue that the levels and distribution are hard to explain with known simple chemistry and might hint at some kind of active process, possibly even life. Others say there are non-biological ways to make ammonia, or that the detections are too uncertain to lean on. So even at the level of is there enough buffering to make droplets slightly less deadly, the debate is wide open. Then in 2020, another chemical signal dropped into this discussion and turned it into a full-blown controversy: phosphine. A team reported a possible detection of phosphine pH 3 in the clouds of Venus at parts per billion levels. On rocky planets like Earth, phosphine is not something you expect to see hanging around in the atmosphere for long. On Earth, you get it from specific industrial processes and from certain types of microbial activity in oxygen-poor environments. It breaks down quickly in air. So if you really see phosphine consistently, you usually assume there's some active source making it. That's why the 2020 claim hit so hard. The team said, "We see a spectral line at a radio wavelength that matches phosphine, and we don't know a good abiotic way to produce that much of it on Venus under current conditions." They were careful. They said it could be unknown chemistry, but the headlines boiled it down to possible sign of life in Venus's clouds. Immediately, other scientists pushed back. Some reanalyses of the same data argued that the signal was weaker than reported or not statistically solid. Others pointed out that sulfur dioxide, a common gas in Venus's atmosphere, can produce a similar spectral signature at that wavelength. New observations with different instruments either failed to see a strong phosphine signal or found levels much lower than the original report. As of now, there is no consensus. Some teams still think there might be a tiny amount of phosphine. Others think the original detection was an artifact or misinterpretation. The key for you is this: phosphine on Venus is not settled fact. It's an open, noisy argument about data quality, instrument calibration, and alternative chemical explanations. It is nowhere near a confirmed biosignature. So why, despite all these arguments, do many scientists take the idea of possible cloud life on Venus more seriously than they take the idea of scorpion-sized organisms on the ground? Because in the clouds, at least the bulk conditions make physical sense. Temperatures of 20 to 60 degrees Celsius, pressures of 0.5 to 2 bar, and radiation levels similar to or lower than what microbes endure in Earth's upper atmosphere. We already know that Earth's stratosphere and upper clouds host microbial life in tiny numbers, cells trapped in droplets and dust that can stay aloft for long periods. So life in an atmosphere is not a crazy concept. On Venus, the acid is the main hurdle. But that is a single brutal problem to solve, not 3 or 4 stacked together. You don't have to deal with solid surface lava temperatures, crushing pressures, and supercritical CO2 at the same time. You only have to figure out how an organism could maintain stable internal chemistry in a hot sulfuric acid environment. That's still extreme, but not as hopeless as the surface scenario. Unknown photochemistry, active volcanoes injecting gases, and lightning could all feed weird reaction networks that might explain things like phosphine without life, or, in a more speculative scenario, might feed life. That's why upcoming missions are targeting the atmosphere and clouds if they care about habitability. NASA's Da Vinci mission is planned to send a descent sphere through the atmosphere, measuring chemistry, noble gases, and taking data all the way down, with a special focus on how the atmosphere formed and evolved. ESA's Envision orbiter will look at both the atmosphere and surface interactions, but with instruments tuned to sniff out gas compositions, trace species, and links between geology and atmospheric chemistry. The idea is simple. If there is any biosignature to find on Venus, it is more likely to be in the pattern of gases and aerosols in the clouds than in a rock right at the surface. So where do the old Venera images fit in once you put all this together? Hellish surface, maybe habitable cloud band, and disputed atmospheric chemistry. They become one part of a larger, messier story. On one hand, the Venera panoramas give us our only direct view of the surface and confirm just how extreme it is. That supports the mainstream view that surface life is extremely unlikely. On the other hand, the whole debate about moving objects did something useful. It forced people to re-examine old data and ask new questions about Venus as a system. When you connect the dots, surface conditions that are almost certainly sterilizing, a mid-cloud region that sits in a plausible temperature-pressure window, and controversial hints like phosphine or ammonia, you don't end up with Venus is definitely alive. You end up with Venus is weird enough that we can't completely dismiss life, but if it exists, it's probably microscopic, airborne, and chemically strange. In that picture, the idea of a 40-centimeter scorpion trudging across a basalt plain next to Venera 13 looks less like the main event and more like a side story. The real question becomes, how do we interpret ambiguous data, whether it's a spectral line in a radio observation or a small blob in a grainy panorama, without letting our desire to find life overrun the limits of the data? To answer that, you have to look at how scientists actually test claims of motion and anomalies in old low-quality images. What does it take to prove that something truly moved in a dataset like Venera's? And how far did the moving object argument really get when you apply those tools? How do you actually prove that something in an old, blurry image really moved, and isn't just your brain grabbing at noise? With Venera, that's the core problem. If you don't use hard, careful methods, you're just guessing. First step is alignment. You can't honestly talk about motion until you're sure every frame is lined up to the same reference. For panoramas, that means you treat them like a crime scene reconstruction. You take two images from different times and you pin them down using fixed features, rocks that obviously haven't moved, the horizon line and parts of the lander that are clearly visible. You mathematically warp and shift each frame so those anchors overlap as closely as possible, often down to a fraction of a pixel. This is called registering the frames. It's not optional. Without it, parallax and scan differences will trick you. Remember, the Venera cameras scan line by line over tens of seconds. A tiny flex in the lander, a small difference in the scan start angle, or a slightly different stance in the soil can make foreground objects appear to jump relative to the background, even if they never moved. If you skip proper registration, you're not measuring motion, you're just watching your own misalignment. Once the images are locked in place relative to solid features, then you look at your candidate object. Does it actually shift relative to the rocks and lander parts that you've pinned, or does it stay with them? If it stays locked to them, that's not motion, it's just part of the static scene. Even if you see a shift after careful registration, you still aren't done. Your brain is very good at saying that looks different. Science doesn't stop there, you have to put a number on different. That means measuring brightness, shape, and size of the patch you care about, and comparing those numbers to the statistics of the entire image. How much does brightness vary across the scene just from noise? How often do you see a dark patch or bright blob of that size and contrast in places where you know there's nothing interesting? If the rest of the image is full of similar blobs that you're happy to call noise, then your special one is probably also noise. You also build simple models of how the imaging system and processing behave. If you take a clean test image and add realistic noise, compression artifacts, and interpolation, do you see similar objects appear by accident? If your model with no real motion can easily generate features that look like your disk or scorpion, then the burden of proof is back on the claim. Without that stats-heavy step, you're basically doing what astronomers did a century ago when they swore they saw canals on Mars because the low-res images kind of lined up with what they expected. Next, you have to ask, is this thing tied to the world outside the camera or to the camera itself? Every sensor has quirks. There are bad scan lines, bands of higher noise, little gain drifts where the signal jumps up or down, and timing offsets where the data clock doesn't quite match the physical motion. Engineers track these behaviors and calibration. They know which lines are weak, which times the heaters cycle on and off, and what the electronics do as they warm. So a serious reanalysis doesn't just look at the pretty panoramas. It goes back to the engineering telemetry, the temperature of the camera, the status of heaters, the timing counters, any error flags. If your moving feature always lines up with a specific scan line that's known to be flaky, or only appears in frames taken when a heater turned on, that's a big clue you're not seeing Venus. You're seeing an instrumental ghost. For Venera, that means checking. Did the camera temperature spike between scans? Did the lander report any mechanical event in the imaging system? Are the suspect pixels sitting on lines that show other oddities elsewhere in the image? That kind of cross-check is slow and not glamorous, but it's the only way to separate hardware behavior from real external changes. Even if an object seems to shift and doesn't match a known instrument glitch, there's still another level of testing. Do any other sensors agree that something happened? The gold standard in this kind of work is convergence. You don't want just a visual hint. You want multiple channels pointing to the same event. On Venus, that would mean, for example, a dark feature changing position in visible panoramas, while at roughly the same time, the microphone picks up an unexplained sound, or the seismometer logs a tiny bump that doesn't match lander mechanisms. Maybe a dust sensor, if you had one, would see a spike. In the Venera case, nobody has shown that kind of multi-instrument hit for any claimed creature. The supposed motions are only in heavily processed images. The seismometers don't show clear local steps or impacts tied to those times. The audio doesn't have a mystery scrape that lines up with a blob moving. There's no extra channel saying, yeah, something physical just interacted with the lander or the ground. Without that, you're hanging everything on one noisy data stream. The cameras. It's not impossible that something real would only show up there. But when you're asking people to accept life at 460 degrees Celsius and 90 bar, 1 weak channel is nowhere near enough. Finally, you have to be honest about history. This is not the first time people have seen strange shapes in planetary data. Planetary science has a whole catalogue of false alarms. Dark branching patterns on Mars that look like forests or trees, and turned out to be CO2 frost patterns. The famous face on Mars, which was just a low-resolution hill lit from a certain angle. Higher resolution images showed a normal eroded mesa. Fluffy bunnies seen by Mars rovers that sparked wild speculation until engineers identified them as bits of insulation or landing debris. Even on the Moon, odd shapes near the Apollo landing sites have been traced back to dropped covers, cables, or camera artifacts. Each of those cases taught the community a hard lesson. Your eyes are not reliable when resolution is low, and you want to see something exciting. The correct response isn't never trust anything, but to turn the bar way up before you say this is new physics or new biology. When you put the Venera moving object claims next to that history, they fit a familiar pattern. Low-res images, strong enhancement and cropping, shapes that become persuasive only after someone tells you what to see, simple engineering explanations, lens caps, scan glitches, parallax, available and consistent with the data, no multi-instrument support, no clean, reproducible signal. So by the standards scientists now use to judge motion and anomalies in old data, the Venera case doesn't pass. You can still find people willing to argue for it, but the mainstream view is that we're looking at hardware, image processing and human pattern seeking, not genuine motion from alien life. But that doesn't make Venera 13 and 14 boring. In fact, once you stop chasing ghosts in the noise and focus on what those landers definitely measured, the real story of Venus that emerges from their data is already extreme enough to reshape how you think about rocky planets. So what did those probes actually nail down about Venus? things we can trust numbers and results that don't depend on reading blobs in grainy panoramas. Strip away the drama about blobs, and Venera 13 and 14 still did something huge. They turned Venus from a fuzzy radar map into a real physical world with numbers you can hang on to. Start with the rocks. Both landers drilled into nearby blocks and fed those samples to their X-ray fluorescent spectrometers. That instrument looks at the energies of X-rays that come back off the sample and tells you which elements are present and in what proportions. The result at both sites is clear. The rocks are basaltic. Chemically, they look a lot like mid-ocean ridge basalts or volcanic plateau basalts on Earth. That single result shuts down a bunch of alternative ideas. It tells you Venus's crust is dominated by volcanic rock, not continental-style granite. There aren't big, light, silica-rich continents like on Earth, floating on top of a different kind of crust. Instead, you've got a world built by extensive lava flows. Combined with impact crater counts and radar mapping, that chemistry feeds into models where Venus periodically resurfaces itself with massive volcanic episodes. Whole regions get buried under new basalt, erasing older geology, so you don't just get a snapshot of two rocks. You get a clue about how the entire planet rebuilds its skin over millions of years. Then there's the soil, or more accurately, the regolith, the loose material on top of the solid rock. Venera 14 carried a surface compressibility probe meant to push into that layer and measure how stiff or fluffy it was. In one of those infamous space history accidents, the probe came down right on a camera lens cap instead of bare ground. So one of the soil hardness readings is actually how hard is our own hardware. On paper, that's a failure, but it's also a perfect confirmation that yes, those bright discs in the images really are lens caps. And Venera 14 still had other ways to feel out the surface. The drill had to bite in. If the regolith were deep and soft, it would have behaved differently. Telemetry from the drill and the lander's response to landing tell you that the surface is relatively firm and rock-dominated, with only a thin, loose layer on top. The upshot is, Venus's plains are not covered by meters of soft dust waiting to swallow landers whole. They're more like solid rock with a bit of grit on top, the way lava fields on Earth often are. That matters for any future mission design. It also tells you that small items like lens caps can just sit on the surface without sinking out of sight. Now what about the air right above that ground? Venera 13 and 14 had pressure and temperature sensors that logged conditions from the descent all the way to the surface and then during their short lives on the ground. Near the surface, they found something surprising. The layer right above the ground is nearly isothermal. In simple terms, temperature doesn't change much with height in the bottom few hundred meters. It's all just very, very hot. They also measured wind speeds of only a few meters per second, think under 10 miles per hour. That's gentle by Earth standards. But remember, this is in an atmosphere about 90 times denser than ours. Even slow air carries significant force. The combination of low wind speeds and high density tells you that the lower atmosphere is dynamically stable. You don't have constant storms or violent mixing at the surface. That stability helps explain why the surface doesn't get endlessly sandblasted, and why rocks and pieces of hardware, like lens caps, can pretty much stay where they land. They might get nudged slowly over time, but they aren't being hurled around. That's another quiet argument against fast-moving, dust-kicking creatures down there. The environment isn't a chaotic hurricane. It's more like a heavy, slow-moving blanket. Then there's the seismic side. The GROZA 2 instrument on each lander acted as a simple seismometer sensitive to vertical vibrations. Venera 13 didn't record any clearly identifiable local quakes during its 127 minutes on the surface. Venera 14 in its shorter run logged a couple of tiny signals that later analysis flagged as possible microseisms, small tremors comparable to what you'd see in moderately noisy areas on Earth. Those hints line up with what radar and other orbital data suggest. Venus is probably not geologically dead. Features like chronae and some changing volcanic vents point to internal activity. The Venera seismic data don't prove active quakes, but they give the first in situ constraints on how loud Venus's deep interior might be at the surface. That's been used to plan future Venus seismology, what instrument sensitivity you'd need, how long you'd have to listen, and how to separate wind noise from real ground motion. Finally, the atmosphere itself. Gas analyzers on Venera 13 and 14, combined with earlier measurements from Pioneer Venus and other missions, nailed down the composition of the lower atmosphere. The numbers are now standard, around 96.5% carbon dioxide, about 3.5% nitrogen, with trace amounts of sulfur dioxide, water vapor, and noble gases like argon and neon. At roughly 92 bars, that CO2-rich mix is what drives the runaway greenhouse effect you heard about earlier. With these ground truth measurements, climate modelers can tune their simulations of Venus and test ideas about how an Earth-like planet could turn into a furnace. Those same models feed directly into how we think about exoplanets that sit close to their stars. The hell world version of Earth we warn about in climate talks isn't hypothetical, it's been measured on Venus, and Venera 13 and 14 supplied key inputs. So whatever you think about the moving object claims, they all sit on top of an environment we actually understand pretty well in bulk. We know the rock type, we know the pressure and temperature profile, we know the near-surface wind regime, we have at least some handle on seismic noise, we know the basic gas mix. The mystery isn't what planet is this. The mystery is whether a handful of tiny anomalies in old images can override all that and demand a brand new kind of high-temperature biology. Before you jump to that, it helps to zoom out even more. Venera's data don't just define one landing site, they plug into a bigger picture of Venus as an active, volcanic, maybe still changing world. And that bigger picture puts even more pressure on any idea of long-term complex surface life. So what does Venus look like when you step back and see it as a whole planet? Its volcanoes, its resurfacing history, its possible present-day eruptions. And how does that context change the odds that anything organised, let alone alive, is creeping around on those lava plains? If you only looked at the Venera landing sites, you might think Venus is just a flat, rocky stove. But when you zoom out with radar, the planet looks more like a giant volcanic experiment that never stopped. Because Venus's atmosphere is so thick and opaque, normal cameras from orbit can't see the surface. You need radar, radio waves that can punch through the clouds and bounce off the ground. That's what the Soviet Venera 15/16 orbiters did in the 1980s, and what NASA's Magellan spacecraft did in the 1990s. Together, they mapped almost the entire planet in radar. Those maps don't show colour, they show texture and slope. Bright areas are rough or angled toward the radar. Dark areas are smoother or turned away. When scientists turned those strips into global maps, a clear pattern popped out. Venus is packed with volcanic features. You see vast lava plains covering most of the lowlands. You see huge shield volcanoes, some larger than the biggest ones on Earth. You see lava channels that run for hundreds of kilometers, like frozen rivers of rock. You also see strange circular or ring-like structures called coronae and arachnoids, broad oval features with ridges and fractures that look like something pushed up from below and then partially collapsed. Combine that picture with Venera's rock chemistry, which shows basalt at the landing sites, and the message is consistent. Venus's surface is dominated by basaltic volcanism, not by the patchwork of moving plates we have on Earth. So you're dealing with a world that builds and reshapes its crust, mainly by erupting lava over huge areas, not by slow plate collisions and subduction. That alone already makes the environment rough on any long-term surface ecosystem. But the next question is this volcano world still active now, or are we just seeing the frozen remains of a dead past? For a long time, the safe answer was probably active, but we don't know how much. Then people went back to old Magellan data and looked more closely. Magellan orbited Venus and imaged the same regions multiple times from slightly different angles. When teams compared those repeat passes carefully, they found changes at some volcanic vents, shapes and radar brightness that didn't quite match from one orbit to another. One high-profile case showed what looks like a vent that changed shape over a short time, consistent with an eruption filling or collapsing part of the structure between images taken months apart. If that interpretation is right, It means Venus had active eruptions in the 1990s, which in geological terms is right now. That would confirm that the interior is still hot and moving, feeding new lava to the surface and injecting gases into the atmosphere. If Venus is still erupting, that could also feed into the weird chemistry debates you heard about earlier. Changing sulfur dioxide levels, possible phosphine, and other trace gases. Fresh volcanic activity gives you a natural non-biological engine for pumping unusual molecules into the air, which then get processed by sunlight and atmospheric reactions. But how often does Venus actually quake and shift, not just erupt? Here the data are thin. We don't have a network of seismometers like we do on Earth. We have those tentative Venera microseisms, models of the planet's interior, and indirect hints from geology seen in radar. Different studies plug in different assumptions about crust thickness, mantle temperature, and how Venus loses its internal heat. Some models suggest Venus might be seismically quieter than Earth. Others say it could be in the same ballpark. What almost nobody argues anymore is that Venus is completely seismically dead. The coronae, the possible recent eruptions, and the internal heat budget all point to at least some level of ongoing activity. For future landers, that's important. If you want to listen for real quakes, you need to design seismometers that can handle the heat and still pick up very subtle motions over hours or days. There's another global clue that Venus hasn't been sitting still: impact craters. When you count craters on a planet, you get a rough clock for how long the surface has been exposed. Venus has relatively few small craters, and the ones it does have are scattered more or less randomly, not clustered in old and young regions. The best explanation is that at some point in the last few 100 million years, a blink in planetary time, large parts of the surface were resurfaced. Maybe not all at once, but likely in a big planet-wide episode, or series of episodes where lava flooded across wide areas, erasing older craters and topography. After that, impacts built up a new, relatively sparse crater population on top of the fresh rock. That kind of catastrophic resurfacing ties into the climate story. If you melt and reset large chunks of crust, you affect how CO2 and other gases move between the interior, the surface, and the atmosphere. A huge volcanic outburst could dump vast amounts of CO2 into the air, helping lock in the runaway greenhouse we see today. Without plate tectonics to cycle carbon back into the interior the way Earth does, Venus ends up with almost all its carbon in the atmosphere, not in rocks. Now think about what all this means if you're trying to imagine any kind of surface life, especially something big enough to show up in a Venera panorama. You're not just asking for life that can tolerate 460 degrees Celsius, 90 plus bar and supercritical CO2. You're asking for life that can also ride out a geologically active planet. Episodic floods of lava, ongoing tectonic stresses, possible quakes, and changes in gas composition over time. That doesn't make life strictly impossible. Earth life has handled volcanism and quakes for billions of years, but here the baseline environment is already on the edge of chemistry as we know it. A macroscopic surface biosphere on Venus would have to be incredibly tough, incredibly adaptable, and able to re-establish itself after large resurfacing events that could wipe out entire regions. That's an enormous extra burden on top of the thermodynamic and chemical challenges you already heard about. So when you look again at the Venera photos, see them for what they really are: brief, fragile glimpses of a restless volcanic world that may still be actively reshaping itself today. Those frames are not snapshots of a cooled, static rock where life could quietly settle in for eons. They are taken on a planet that melts and repaves its own skin on geologically short timescales, under an atmosphere tuned to trap heat. That context doesn't prove there's no life on or around Venus, but it does make the idea of a long-lived, complex, surface-dwelling biosphere much harder to defend. And it shapes what space agencies decide to build next. If you're going back to a world like this, what do you send? Another short-lived lander, a long-duration seismology station, or orbiters and probes that focus on the atmosphere where life, if it exists, might actually have a fighting chance? New missions are lining up to go back into this furnace, But look at what they're actually built to do. They're not hunting scorpions on the ground. They're aimed at the atmosphere, the geology, and the deep history that turned a near-Earth twin into a furnace. Start with Da Vinci. NASA's Da Vinci mission is planned to launch near the end of this decade, with a dive into Venus's atmosphere a couple of years after that. It carries an entry probe in the shape of a descent sphere, not a lander. That sphere isn't trying to survive on the surface for hours. It's designed to fall through the atmosphere once, sampling all the way down. On the way in, Da Vinci will measure the mix of gases at different heights, especially noble gases like argon and xenon, plus water, sulfur species, and other trace components. Noble gases matter because they don't react much, so their ratios preserve information about how the atmosphere formed and evolved. It will also take high-resolution measurements of temperature and pressure as it descends, giving the best vertical profile since the Venera and Pioneer Venus days. The focus is origin and evolution of the atmosphere, not life and not surface imaging. But those profiles will tighten every model we use to say how fixed or violent the lower atmosphere actually is. Then there are the new radar orbiters, Veritas and Envision. These are about seeing the whole planet in sharper detail than Magellan ever could. Veritas, a NASA mission, is planned to carry a modern radar system that can map Venus's surface at higher resolution and with better elevation data. It will also use spectroscopy to study surface minerals and look for changes over time, signs of active volcanism or tectonics. Right now it's on a no earlier than early 2030s track, pushed later by budget issues. But if it flies, it will be the best tool yet for checking whether vents are actually changing, whether lava is still flowing, and how heat and gases move from the interior to the atmosphere. Envision from ESA is a separate but complementary orbiter. It will also use advanced radar and spectrometers to image the surface and probe the planet's interior structure. The idea is to see how Venus's crust and mantle behave, how thick the lithosphere is, and how resurfacing and tectonics work without Earth-style plate motions. Both missions target tectonics, volcanism, and possible present-day activity. They are built to answer how alive is the geology, not is there a thing walking around by this rock? What about actually going back to the ground? Russia's proposed Venera D mission is the big concept there. The plan on paper is an orbiter plus a long-lived lander, and maybe balloons in the atmosphere. One of its stated science goals is to look for potential microbial life in the clouds, following up on controversial hints like phosphine and ammonia. If it gets funded and built, it would be the first mission since the Soviet era to touch down on the surface of Venus and try to survive there. The D in Venera D stands for Dolgojivushchaya, long-lived. That tells you the ambition, not a 60-minute death race, but something that can last long enough to do real seismology, detailed chemistry, and long time series of temperature and wind. But Venera D is still a proposal, not a guaranteed mission. Timelines hover in the mid-2030s at best, and they depend heavily on funding. Still, the fact that it's even on the table shows that people are serious about returning to the inferno with better gear. All of this talk about new missions sits under one hard reality: budgets. NASA, ESA and Roscosmos are all juggling multiple priorities: Mars, the Moon, outer planets, Earth science. Officials have already said straight out that not every Venus mission may move forward exactly as planned. Veritas has been delayed. Envision's instruments depend on international cooperation and money that isn't locked in forever. Da Vinci has to stay on schedule in a crowded launch queue. There's a lot of talk about a decade of Venus, but it's a decade under pressure, with every mission having to prove its value. Still, agencies keep pushing. The scientific payoff is big. Understanding why Earth and Venus, two planets so similar in size and bulk composition, ended up so different is central to exoplanet science, climate science, and basic planetary physics. And if there's any chance that clouds on Venus could host even strange acid-tolerant microbes, that's a huge motivation to keep going. Now look at what's missing from all these plans. Nobody is building a camera specifically to look for animal-sized life on the surface. No mission concept says, we're going to park next to the old Venera sites and wait for something to walk by. New lander designs, where they exist, emphasize rugged seismometers, improved rock and soil chemistry analyzers, and long-duration environmental monitoring. If they carry cameras, and they almost certainly will, it's to document geology, hardware, and context. If they happen to re-image a Venera landing area, it'll be to see how rocks and surfaces differ, not to run a creature census. That tells you where the expert bet is. The community's working assumption is, if Venus hosts life anywhere, it's in the atmosphere, in microscopic or small airborne forms, not in big surface organisms strolling past a Soviet lander. The surface is still science target number one for geology, heat flow and climate history, but not for biology. And yet the old Venera moving object story still matters. Not because most scientists think it showed aliens, but because it exposed how easy it is to overinterpret marginal data, and how important it is to get your methods right before yelling, "Life." That's not just about Venus. It's training for what's coming next, when we start seeing equally faint, ambiguous signals from planets around other stars. So what's the real lesson you're supposed to take from this story? When you put the hellish surface, the maybe habitable clouds, the disputed gas signals, the old Soviet panoramas, and the new missions together, what does it actually say about how close we are, or how far we still are, from being able to say with confidence we've seen life beyond Earth? This whole something moved on Venus story sticks around not because the evidence is strong, but because it's a perfect example of how science is supposed to handle wild claims under pressure. Look at what actually happened. One scientist, Ksanfomaliti, goes back to low-quality, heavily processed images from the early 1980s and makes an extraordinary suggestion. Some small shapes might be moving in a place where mainstream science says nothing alive should exist. He publishes his analysis. He labels features, measures sizes and times, and proposes possible manifestations of life. Nobody bans the paper, nobody says you're not allowed to ask that. Instead, other experts step in and do exactly what you'd want them to do. Engineers who know the landers check the hardware and say, "That bright wandering disk, that's just our lens cap." Image specialists reprocess the data and show that the scorpion only really pops out after extreme sharpening and interpolation, and fades in cleaner versions. People compare positions, lighting, and timing, and find that simpler explanations, lens caps, scan artifacts, parallax, noise, line up better with the evidence. The key is, the wild idea isn't automatically thrown out because it's wild. It's tested against boring, hardware-based explanations, and right now, the boring explanations win. That's scientific skepticism in action. The burden of proof sits squarely on the extraordinary claim, and until the evidence is strong enough to beat the simple story stays. At the same time, the episode shows why old data sets are still worth digging into. Venera 13 and 14 flew in 1982. For decades, their images and telemetry just sat in archives. Ksanfomaliti's paper, even if you think his conclusion about life is wrong, forced people to go back, find better copies of the data, and reanalyze them with modern tools, better image processing, better geometric registration, more realistic noise modeling. That pattern isn't unique to Venus. Apollo seismometer records have been re-examined with modern computing and revealed subtle moonquake patterns we didn't see at first. Viking lander data on Mars have been reprocessed to squeeze out new chemical insights. Old Magellan radar swathes were revisited to spot possible recent volcanic changes. Venera is now part of that same tradition. Legacy missions that keep paying off scientifically when you point new tools at them and ask fresh questions. This is also rehearsal for something much bigger, reading signs of life on planets we will never visit in person. Look at the phosphine argument on Venus. One team says, "We see a sectoral line that looks like phosphine. We don't have a good non-biological source, so maybe life." Other teams say, "Your data reduction is off," or "That line is actually sulfur dioxide," or "If phosphine is there, it's at much lower levels than you think." The back and forth gets technical, calibration, baselines, alternative models. Now scale that problem up to exoplanets. There you might only get a few pixels of data or a single faint spectral line from a world dozens of light years away. If we can argue this hard about chemistry in the clouds of a planet right next door, with multiple probes and decades of context, imagine how careful we'll have to be when someone claims biosignature gas on a remote super-Earth. The Venera creature saga and the Venus phosphine fight are both training runs for that future moment. They're reminders that most first hints of life will sit right on the edge of what the data can reliably tell us. There's also a shift in how you see Venus itself. You probably started with the simple picture. Venus is Earth's evil twin, same size, same bulk composition, but totally dead under a crushing hot atmosphere. Then the details start to pile up. The surface is volcanic and probably still active. The clouds have weird chemistry and maybe, just maybe, conditions that brush against what some microbes could tolerate. Old Soviet images, when pushed hard, produce ambiguous shapes that some people are still willing to fight over. The real shock isn't that aliens casually posed for Venera 13 and we all missed it. It's that in 2026, with all our instruments and models, Venus is still not a closed case. We can say surface life is extremely unlikely with confidence, but we can't absolutely rule out more subtle, stranger forms of life higher up. We can't fully explain every blip in its atmospheric chemistry. Our nearest planetary neighbour is still weird enough that truly ruling out wild ideas takes serious work. And that leads to the main takeaway. When you hear Soviet probe photographed something moving on Venus, don't stop at the clickbait. Underneath that line is a layered story. The brutal engineering of pressure hulls and sacrificial cooling, the chemistry of supercritical CO2 and basalt plains, the image processing details of line-by-line cameras and lens caps, and the argument between exciting but fragile claims and solid but boring explanations. Mystery in this context isn't magic. It's just data we haven't fully explained yet. Sometimes when you dig in, the mystery dissolves into lens caps and noise. Sometimes it points you to real gaps in your understanding, like why Venus's atmosphere looks the way it does, or whether its clouds could host something living. The lesson from Venera is simple and hard at the same time. The next time something seems to move in a distant dataset, whether it's a pixel on an exoplanet or a glitch in an old probe's camera, we have to push through the same grind, alignment, calibration, cross-checks, before we dare attach the word life to it. Because as you've just seen with Venus, the universe doesn't just hand us answers, it hands us noisy, half-broken signals from hostile places, and we have to earn every conclusion we draw from them. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.